Hello, this is Steve Goff. I'm a fluvial geomorphologist and owner of Little River Research and Design, where the clip you're about to see was made. We made these clips with US EPA 319 funding and support from the Missouri Department of Conservation and Natural Resources. We're going to mine some gravel today with this demonstration. Using an aspirator here, we're going to create a pit in the center of the channel. And immediately you can see, as indicated by this yellow arrow, a head cut migrates upstream. And the channel is incising as this head cut moves through. By digging this pit, we've effectively increased the local slope and thus the channel's capacity to move sediment. And we're seeing a lot of erosion because of that. The channel is incising, and the sediment created by the erosion and incision is refilling the pit. Now, a pit like this also severely disrupts sediment transport continuity. And a lot of sediment is entering the pit, but almost none is coming out. And this creates a hungry water effect downstream, which causes the downstream channel to incise and blows out riffles. You can see the channel is migrating towards the top of the frame upstream of the pit and leaving behind a series of terraces that indicate that it's downcutting. And you can see these features in the field upstream of gravel mined area, for example, and use them to diagnose this process. The pit's slowly refilling. We're going to see dye pulses move through that give you an idea of the relative speed of flow in the channel and also of relative depths. The darker the hue of the dye, the deeper the flow. We often speed these clips up. We time-lapse them. But this one is running at that real time. It's not been speeded up at all. And next we're going to demonstrate floodplain or bar pit mining, which is an alternative to mining directly out of the channel that can be much less damaging, but probably can be even more damaging when the pit is captured by the main channel, which happens pretty frequently, especially when the pits are close to the active channel. Here we see the channel capturing that pit, violently causing a head cut to migrate upstream again as local slope is increased. The pit's going to rapidly refill here. Note the sediment blowing out downstream of the pit from the hungry water effect. So we've got incision upstream and incision downstream as well. And if this were a real-world situation, we would be creating a pretty awful unstable habitat situation throughout this entire reach. And of course, we've left behind the channel that we started with at the bottom part of the frame. The material we're using for this simulation is ground melamine plastic. It looks a lot like coffee grounds, with the exception of its lighter color. And it has a specific gravity of about 1.7, only about half again as much as water. And so it gives us a much better simulation of these processes than sand or gravel would, which is the material you've traditionally seen in stream tables. Now, as the simulation runs on, you'll see that we will slowly regain sediment transport continuity. In other words, the sediment transport rate at cross sections all along the channel that you see here is roughly the same. And that's one definition of stability. It's one that I like. And as the river settles down a little bit and reestablishes sediment transport continuity, you'll slowly see the dye pulses will help you'll see the establishment of a gently meandering single thread channel. Again, this is Steve Goff with Little River Research and Design, where we made these clips using an mriver river model. You can find us on the web at emriver.com. That's emriver.com. We hope you've enjoyed this, and thanks for watching.